As part of secondary metabolism, plants produce aromatic compounds that are isolated in the form of essential oils via the distillation process. Essential oils are volatile. At room temperature, they are usually liquid mixtures of monoterpenes and monoterpenoids, sesquiterpenes and sesquiterpenoids, and phenylpropanoids. According to the functional groups in the molecules, they are classified as aliphatic compounds, carboxylic acids, alcohols, ethers, esters, and aldehydes. Essential oils are highly soluble in lipids and lipophilic organic solvents, have a large refractive quotient, and are optically active. They usually have a lower density than water, with some exceptions such as cinnamon, cloves, sassafras, and vetiver essential oils. In nature, essential oils are most frequently found in so-called higher plants. Pharmaceutically important are especially essential oils of the pine, umbellifer, laurels, myrtles, aster, mint, and citrus families. Essential oils are found in all plant organs or parts, in flowers, roots, wood, leaves, and in the rind, rhizome, fruits, and seeds. The organs of plant species may contain an essential oil that differs in composition. For example, bitter orange, Citrus aurantium ssp. aurantium, contains essential oil in the pericarp, flowers, and leaves and shoots. Essential oils from the aforementioned parts are different in composition. Essential oils of plants of the same botanical species growing in different geographical areas or different conditions differ considerably in their chemical composition. Vegetable metabolism is already highly dependent on many environmental factors, and essential oils are an example of metabolites where the variability in composition is greatest. The term essential oil chemotype is also based on this characteristic. Each chemotype is defined by the dominant component or component that is characteristic of the essential oil. The most well-known chemotypes are in the essential oils of plants of the family of mints, Lamisaceae. For example, there are 6 chemotypes of thyme essential oil, 4 chemotypes of essential oil of basil, and 3 chemotypes of rosemary essential oil. The essential oil content of selected herbal drugs is determined by the method set out in the European Pharmacopoeia. That method is based on the aqueous distillation of essential oils. Performing an analysis depends on the herbal drug. It is therefore necessary to follow the procedure prescribed in the pharmacopoeial monograph for the herbal drug analyzed. Herbal drugs are distilled using the Clevenger apparatus. This is not intended to obtain larger quantities of the essential oil, but to accurately measure its content. It is basically a distillation device which, through an additional inclined tube, allows us to return the condensed aqueous phase to the sample flask. Since water circulates through the system during distillation, the plant sample can be distilled for a longer period of time in a relatively small amount of water. A certain amount of essential oil is always distributed or lost in the aqueous phase, and if the volume of water is smaller, this loss is also smaller. Place the prescribed amount of demineralized water in the flask of specified volume and add the boiling chips. Install the Clevenger apparatus. Fill the apparatus with the mineralized water to the top through the funnel. It is important that the triple valve is pre-turned to the upper position, so the upper pipes are connected. Remove the upper plug on the adapter and pour the prescribed amount of xylene into the apparatus using pipette. Reinstall the plug so that the notch in the plug is aligned with the opening on the deck. Heat the mixture in the flask to the boiling point and determine the distillation rate, which should be 2 to 3 milliliters per minute, unless otherwise prescribed. The distillation rate is determined by draining water from the apparatus to the lower edge of thickening of the tube. Close the valve and measure the time it takes for water to reach the upper edge of thickening of the tube. The thickening volume between the two edges is 3 milliliters. The valve is then opened and distilled for another 30 minutes, and the heating is adjusted to obtain the required distillation rate. After 30 minutes, stop heating and record the amount of xylene in the graduated tube after at least 10 minutes of cooling. This is volume 1, which we will need when making the final calculation. The volume of the entire graduate tube is 1 milliliter. In the aqueous phase, some xylene was distributed during the first distillation. As a result, the aqueous phase is saturated with the organic phase. Thus, at the next stage of distillation of plant sample, lipophilic substances cannot be further dissolved in water. In this way, an even more accurate final measurement is obtained. Add the prescribed mass of the herbal drug to the flask and proceed to distillation according to the procedure described above for the prescribed time. Then stop heating and re-record the xylene volume in the graduated tube after at least 10 minutes. This is volume 2. In some plant specimens, a change in the color of the organic phase as a result of dissolved essential oil can also be observed. Chamomile essential oil, for example, has an intense blue color due to the compound called chamazulane. The quantity of essential oil in the plant material is determined from the difference between the volume of the organic phase measured at the end of the volume of xylene measured at the beginning of distillation. The content of essential oil in the herbal drug is given in milligrams per kilogram. The calculated amount of essential oil is compared with the prescribed amount in the pharmacopoeia. An herbal drug is suitable if it contains at least the required amount of essential oil.